Greetings to you. Welcome to the next class. We are having different types of electrodes for comparison, and there are different types of electrodes. One is a metal in equilibrium with its O ions. Okay. So, here I have a zinc metal. I have a zinc metal in the oxidized state, okay, that is carrying +2 charge, that can react with 2 electrons. It can pick up 2 electrons and become zinc metal, that is reductant. So, oxidant plus electrons gives you reductant. I should write 2E minus here, okay, but it is not there. Please make a note. Zn2 plus 2E minus should give you 2 plus, and 2E minus should give you 0. So, we do not write 0 here, but it is zinc reductant. So, E naught is equal to the, when I compare with hydrogen as a inert electrolyte, I get a voltage of minus 0.763. So, hydrogen is a reductant. Okay. So, zinc is also a reductant because it is minus. Okay. So, zinc metal is a reductant, zinc 2 ions are oxidized species. Similarly, I can take copper ion, copper solution, and then reduce copper using an inert electrolyte, okay, that is standard hydrogen electrode. And what reaction takes place in that case? Cu2 plus in the oxidized state, that is ions, cupric ions will react with 2 electrons, and that goes to cupric metal, copper metal, and the potential what I get is 0.337 volts when I compare it with hydrogen. So, we by convention we get assign hydrogen as 0. So, I measure 0.337 volts. Similarly, I can take silver ions, silver nitrate in solution, react it with an electron. So, it gives me silver reductant, and E naught is equal to 0.799 volts. So, E naught values are quoted in voltage relative to SHE, standard hydrogen electrode, at 25 degrees. The expression what I write is EA is equal to E naught A plus RT by NF ln A oxidant. Here you should see that I am not writing reductant here at the bottom, correct. So, but theoretically I should write, but the convention is whenever an ion is reduced to its metal, its activity is 0. Okay. So, log 0 is 1. So, instead of writing log activity of the reductant as 1, I simply write ln AOX, that is the ion in solution. So, what does it mean? The actual potential what you get when compared with a SHE is nothing but the standard reduction potential plus RT by NF ln of log of concentration. I am not writing activity also now. Actually I should write activity, but activity and concentration, if they are almost same, if the solutions are dilute. So, I am writing a concentration term of the concentration of the solution. A oxidant is the concentration of the solution. When it is getting reduced, I do not write the denominator. So, this is a very standard practice. You should all remember this. I am quite often in my future this thing I will not be writing this. So, a metal that is one kind, that is a metal in equilibrium with its own solution, okay, in equilibrium with its own solution, a metal wire, rod, electrode in equilibrium with its own solution coupled to standard hydrogen electrode. So, whatever EMF value, potential value I get, I list. So, that is how I got. For zinc it is 0.763, for copper it is 0.337, and for silver it is 0.799. For zinc it is negative, that means hydrogen electrode becomes positive in this case, here it is negative. Okay. Then I have another type of electrode. That electrode we define like this: a metal in equilibrium with a saturated solution of a slightly soluble salt. That means, I have a metal wire as an electrode that is dipped in a solution, okay, and that substance solution contains a sparingly soluble salt solution. The best example I can give you is silver chloride. You take silver chloride, put it in water. So, a little bit of silver chloride will dissolve, remaining will be settling at the bottom, and I dip a silver electrode in that solution. So, a silver electrode dipped in a solution of silver chloride is an electrode of the second type, okay. Because it is a sparingly soluble salt, it is a saturated solution. Okay. So, in this case again it is connected to standard hydrogen electrode, that I am not writing here. Okay. So, what is the reaction now? I have a silver chloride salt that can pick up an electron, that is Ag plus electron. This AgCl will give you Ag plus and Cl minus. Okay. So, this silver will react with one electron to give you silver metal and chloride ion. So, the potential for this at activity is equal to 1, that means very dilute concentrations, E naught is equal to 0.2221 volts. So, similarly I can pick up other sparingly soluble salts, for example, Hg2Cl2, mercurous chloride. This is known as mercurous chloride, that is also sparingly soluble salt. If I take mercurous chloride in water and put a mercury electrode, I have a electrode of the second kind, that is metal in equilibrium with a saturated solution of slightly soluble salt, and Hg2Cl2 plus E minus, I can write an equation 2Hg plus 2Cl minus. So, I should have 2 here. We are not writing stoichiometric equation. So, but you can write 2 here. Hg2Cl2 plus 2E minus will give you 2Hg plus 2Cl minus, but it does not alter the voltage. Okay. So, E naught remains the same whether you write 2 or 1, because we are writing only an equation. So, E naught is equal to 0.2676 volts at activity of 1, that is very dilute solutions. So, half cells of this type are used as reference electrodes and known as secondary electrode standards. I will explain to you later, just give me a few minutes, I will explain. These are easy to fabricate and reproducible and have low temperature coefficient. Now, imagine how do I prepare a secondary electrode of this type? Take a solution, put a little bit of silver chloride and put one silver electrode, that is it. But it gives me an exact voltage with respect to hydrogen, that is 0.2221. But standard hydrogen electrode we make by first taking a solution and then putting a platinum electrode, passing the hydrogen gas, that should be at 1 atmosphere, and then it should have certain amount of acid etc. to keep the reaction going. So, instead of that, this I can use it as a reference electrode instead of hydrogen electrode, very easy to make with respect to hydrogen. You need a gas cylinder, open it, operate it and all those things, and people are not comfortable preparing having a standard gas electrode in the laboratory, because you need a hydrogen cylinder, anytime it may explode if people are not careful. So, it is a little tricky to have standard hydrogen electrode. Only for very accurate work, R&D labs, research labs, yes, it can be done. But if I know that this silver chloride electrode is having a potential of 0.2221, I can connect it to any other system instead of standard hydrogen electrode and subtract 0.22221. Then that gives me the standard electrode potential, not standard electrode potential, but actual electrode potential. So, this is used to replace standard hydrogen electrode, that is the electrodes of the second kind. First kind is a electrode with its own solution, but that salt is soluble in large quantities, that is number 1. Number 2, a metal ion with a sparingly soluble salt with precipitate below and the electrode, metal electrode. Third one is we can prepare this half cell. No, before I go to the third one, we can have two types of reactions with respect to Hg2Cl2, that is I can write something like this: Hg2Cl2 plus 2 electrons goes to 2 Hg plus 2 Cl minus, that goes to 0.246 versus saturated KCl electrode. This is a reference electrode now. This saturated KCl, saturated calomel electrode it is called as Hg2Cl2 plus 2E, and if it is saturated, it will give me voltage of 0.2446, but if it is not saturated, then it gives me 0.222. Saturated will give me 0.246. Okay. So, Hg2Cl2 plus 2E will also give me 0.280 versus NC, national standard. AgCl also will give me 0.237 in KCl solution, 1 molar KCl solution, it gives me 0.237. Again it is a sparingly soluble salt of the second type, and it gives me reproducible value every time I put silver chloride in a solution and put a silver resin. So, the first two type, this type is known as standard calomel electrode, and this is silver chloride electrode. Okay. And then I have another kind, that is third one, that is two soluble species in equilibrium at an electrode, at an inert electrode, say platinum. So, here I have a small problem. The oxidized state and the reduced state both are in solution. You can imagine iron. Iron can be in ferric state, it will dissolve quite in large quantities, that will be brown in color, and iron solution can also be in ferrous state plus 2 oxidation state, that is light green in color. So, if you take iron ferrous, that is green color, oxidize it, it will become brownish color. Okay. So, both the oxidized state as well as reduced state is in equilibrium, are in equilibrium, but they are in of different color, they are in solution. So, when so far I had explained to you that any oxidation state to reduction state, when it is reduced, it should go to metal. That is not always true. What is true? It can go to reduced state, and that also can be a solution. In such cases, I cannot have a reduced species metal ion, metal electrode. I cannot have Fe2 plus, I can have only iron electrode. Okay. So, in such cases, I can write an expression when such systems are examined with respect to electrode standard electrode potential. I get Fe3 plus E minus going to Fe2 plus, and E naught is equal to 0.77 volts with respect to standard hydrogen electrode. But then if what kind of cathode I should have here? The question comes, what kind of cathode we will have here? The point is we can have a platinum electrode. Platinum electrode to pick up electrons from ferric to ferrous, ferrous to ferric equilibrium in the solution. Whenever the released electrons will be picked up by the platinum electrode and transferred to the outside circuit. So, that is the kind of third electrodes of the third kind. So, first is electrodes of the first kind is a metal electrode with its own solution, which is quite soluble. Second is a metal electrode with a sparingly soluble salt, that is second kind. And third is a a platinum electrode with two species in solution which are not platinum. They could be anything, ferrous ferric, iron that is cerous ceric, or it can be manganous manganic, it can be anything. So, I can also write another equation Hg2 plus going to Hg2 plus, Hg1 plus, it should be 1 plus here. So, 2 Hg1 plus 2 E going to Hg2 2 plus. Okay, this is mercurous and mercury. Here there is an error here, it should be 1, that is mercurous to mercuric. This is ferric to ferrous. Okay. So, here it is mercuric to mercurous, other way around, sorry. So, 0.920, and here it is ceric to cerous. I told you, we are going to write everything as reduction potential. So, ferrous ceric to cerous is reduction, cerous to ceric is oxidation. So, here we are going to write everything as a reduction reaction, and the standard electrode potential what with respect to NHE standard electrode SHE standard hydrogen electrode is 0.771, 0.920 and 0.161. The only function of the electrode is to transport electron to or from the ions in the electron. Okay. So, these are the three kinds of electrodes normally we employ in our electrochemical studies. So, we have described three types of electrodes, and one is metal in its own solution, metal in a equilibrium with its sparingly soluble salt, and a redox species in the solution with two platinum electrodes or one platinum and one hydrogen electrode. Okay. So, now I talk about the sign convention. As I said earlier, E naught values are known as standard electrode potential, and if copper and zinc electrodes are constructed, look at the data here now. Here I am writing zinc 2 plus 2 E minus as zinc. This is one half cell reaction, and E naught is 0.763 with respect to SHE, and hydrogen electrode is H2H plus 2 E minus going to H2, and that is E naught is equal to 0.0. In all these cases, we assume that concentration activity coefficient is 1 and concentration is equal to equivalent to activity. Then I can write another equation Cu2 plus 2 E minus goes to Cu, and E naught is minus 0.337 volts. So, if copper and zinc electrodes are constructed if I take one copper electrode and one zinc electrode, put them in two beakers, put two copper electrode and zinc electrode, okay, connect them from outside, copper ion is found to be positive with respect to zinc. Why? Copper is minus 0.337 volts, whereas zinc is minus 0.763. You construct a scale minus 0.763, minus 0.337 and then come to 0, then positive values. So, minus 0.337 is positive with reference to zinc. So, if I have copper and zinc solutions with their electrodes connected from outside, zinc is found to be negative compared to copper, and that will be reflected in the potentiometer, voltmeter, whatever it is. Okay, this is the convention. So, even if I know that copper is going to be deposited on zinc, okay. So, the writing is only on the as reduction reactions. I am not writing both of them, one as positive reaction. Actually, I should write Zn2 plus 2E minus going to plus Zn2 plus Cu2 plus going to Zn and zinc. Okay. So, the half cell reaction if I connect this, I will get a difference of about 0.763 minus 0.337, that is approximately 0.3 volts, 0.4 volts. Okay. So, that is the utility of sign convention. Henceforth, please write all electrochemical reaction as reduction reaction, that is the message. Okay. So, we define a term what is known as reversibility. A half cell is said to be reversible, half cell, okay, not full cell. Half cell is said to be reversible if a change in the direction of current flow, that is I change from outside the switches positive to negative and negative to positive, I just exchange them, then the reaction proceeds in the opposite direction. So, most of it the half cell reaction also should reverse. So, that is if oxidation is taking place on one side, I change the polarity outside, then the reduction will be taking place in the solution. So, such a system is known as reversible reaction. So, most of the half cells act reversibly in normal circumstances. So, consider zinc and AgCl system. Again zinc going to Zn2 plus 2E minus is the reaction. This is we are writing as reduction potential, reduction reaction, and 2E minus plus 2Ag goes to 2Ag plus zinc 2 plus 2Cl minus. Okay. So, this is the reaction, and I am combining this reaction also here. So, zinc 2 plus on the right hand side I have zinc ions and silver ions and chloride ions, and if this cell is connected to a source of electricity at high voltage to force current in the wrong direction, in the reverse direction, that means I change the polarity, the reaction is going to be 2H plus 2E minus going to H2 and 2 silver plus 2Cl minus is going to precipitate as silver chloride. So, the overall reaction is nothing but 2Ag plus 2H plus 2Cl minus, that is already there. So, this will form AgCl silver chloride and hydrogen. So, instead of deposition we are going to have release of hydrogen. So, it is seen that silver chloride is reversible, but not zinc HCl solution. Okay. So, what happens if zinc HCl solution I change the polarity, hydrogen will be released. If I change the polarity again, zinc will be deposited. So, this you should understand about the reversibility, but most of the reactions are reversible in electrochemical sense. So, this I have already explained to you that an electrode is said to be polarized if its potential is in variance but now we are talking about the potential, not the voltage, and we are talking about the electrode. So, electrode is said to be polarized if its potential is in variance with the Nernst equation. So, what does Nernst equation say? E is equal to E naught minus R T by N f plus R T by N f ln oxidant divided by ln reductant. So, ln reductant is 1. So, ln oxidant E is equal to E naught plus R T by N f ln A oxidant. Okay. Now, whatever is the value depends upon E naught is fixed constant. Okay. So, the potential will be should be proportional to the concentration. I will go back just momentarily for your convenience for that reaction. Here E A is equal to E naught A plus R T by N f ln A oxidant. For any reaction, for assume that this is for the electrode, zinc and zinc Zn2 plus electrode, I write E naught zinc zinc 2 plus Zn by Zn2 plus. This is constant with respect to standard electrode potential with respect to SHE. But then what will be EA? EA is will be in, depends upon the concentration of the solution, isn't it? So, R is constant, T is constant, number of electrons are constant, Faraday is constant. So, only thing that can vary is concentration of the solution. So, actual potential depends upon the concentration of the solution, and if the concentration, if the actual potential is in difference, it is in variance with the calculated value like this, they are taking into account concentration, what I should get. If I do not get it, then I say electrode is polarized. Okay. So, that is the concept of polarization. So, an electrode is said to be polarized if its potential is at variance with the Nernst equation. That means, you calculate with respect to concentration, add E naught, and if it is not the same actual potential what you measure in the voltmeter, then it is electrode is polarized. This happens quite often whenever there is a poisoning of the electrode, and then sometimes deposition, so many other reasons are there, we will go into that later. So, this polarization of the electrode may be due to changes in the actual concentration of the ions at the electrode surface, that is known as concentration polarization. Sometimes changes occur due to actual concentration, not at of the activity at the electrode surface, then it is known as concentration polarization. If the concentration is the reason, then it is known as concentration polarization. So, over voltage, again I have defined it number of times, and according to thermodynamic definitions, any half cell that is operating irreversibly if appreciable current is flowing, it is always greater than the corresponding reversible potential as calculated from the Nernst equation. The difference between the equilibrium potential and the actual potential is known as over voltage. That is the difference. Whenever we say an electrode is polarized, what is the quantity of voltage that is different, how much it is different it is. So, that potential is known as over voltage. It is essentially the extra driving force necessary to cause a reaction to take place at an appreciable rate. So, of special importance is the over voltage due to hydrogen ions conversion to hydrogen gas, which would take place at 0 volts if no over voltage is applied. Okay. That means, conversion of hydrogen ions to hydrogen gas should take place at 0 volt, but it has to happen when there is no over voltage. But if you have to apply over voltage, that means the other electrode is polarized. So, you have to apply that much of extra voltage to get the hydrogen gas. Okay. So, ferric and zinc 2 plus can be reduced to free metals at mercury cathode, even though their standard potentials are more negative than standard hydrogen electrode. Now, a little bit of chemistry, because ferric and zinc ions can form amalgams with mercury. So, they can many elements can form amalgams with mercury. So, we can use them with mercury cathode, many elements. So, their standard potentials are more negative than standard hydrogen electrode, because hydrogen electrode is 0, nothing can be less than 0 in real life. So, because the high over voltage of hydrogen ion on mercury pressure liberation, that is the reason. So, at a platinum cathode these ions cannot be reduced from an aqueous solution, as the potential cannot exceed that required for hydrogen liberation. So, based on these information, we have different kinds of electroanalytical techniques. One is potentiometry, that is direct application of the Nernst equation through the measurement of potentials of non-polarized electrodes under condition of 0 current. We equate concentration and potential when there is no current is passing. Okay? That is 0, that is known as potentiometry. Voltammetry, I do apply a potential across a pair of electrodes, one of which is a non-polarizable electrode, that is reference electrode, the other one is polarizable inert electrode. The current that flows must be dependent upon the composition of the electrolyte, and I determine the composition of the electrolyte depending upon the current that is being produced. So, if the other electrode is a dropping mercury electrode, then we call it as polarography. This is part of voltammetry only. So, amperometry is similar to polarography, but both electrodes are polarizable. Usually current voltage curves are recorded in these studies. Then conductivity we have already studied a little bit, and oscillometry, changes in the conductance and other properties by using high frequency AC, and then coulometry is Faraday's laws of electrolysis applied to electrodeposition, that is electroplating. Chronopotentiometry is recording of the transient current movement flowing immediately after closing an AC circuit before it attains equilibrium, that is chronopotentiometry. All these things are different types of electroanalytical techniques, and we will be studying them in detail, not all, but potentiometry and voltammetry, and then we will move on to other subjects that we will study in our next class. Thank you very much.